Hi everybody, welcome back to Chem 121. We are, oh, sorry, there's a cat right in my ear. We are continuing on chapter 9, and we are going to try and finish that up today so we can do chapter 10 next week, which is the last chapter. Oh, my cats are fighting, hold on. Stop! I didn't hit mute, sorry about that. That was why I heard cats. They were fighting in the hallway. I don't know what's with them. Stuff that's coming up. So lab worksheet number 4 is due tonight. Tonight's last call. Make sure you get that in by the deadline. Let's see here. Course evaluations are currently open. Check the announcement about course evaluations. I sent a link out to each individual section that only works for that section, so make sure you follow that link. Doing the course evaluations can get the class a small amount of extra credit, so please do that. And then finally, I didn't really have enough space to fit this in here. But lab worksheet, or I'm sorry, not lab worksheet. Quiz number 8 will be due on Tuesday and then close Wednesday so that I can open it up on Thursday. If we finish chapter 9, actually, regardless of whether we finish chapter 9 or not, I'm going to do the same thing for chapter 9's quiz. So both quizzes will be due on Tuesday and close Wednesday so that you have them open on Thursday so you can study them for the exam. Exam number 2 is on Friday. So we're going to get started in just a second. I had to deal with the cats, so give me a second. Well, I went in the other room to check what all the sound was, and they're both just sitting there innocently, like, we would never do anything wrong. Also, hello. I'm like, sure, Jan. Okay, so let's talk about a specific type of class of reactions called redox reactions that are going to be useful in biology because redox reactions are a special category of reactions that involve electrons. Now, we did a lot of oxidation reduction or redox reactions already in this class, but we didn't actually say that this is what was going on. But now that we're this far and we've covered so many topics, we can actually say that in a reaction where electrons are moved from one reactant to the other, we can call a redox reaction. So the first one of those that we did, oops, I don't want this plus here, was way back in the ionic bonding chapter. That was chapter 4, where we did something like this, where I had sodium and chlorine, and I said, okay, well, I'm going to take this electron off of sodium and give it to chlorine. This would be a redox reaction, because not only are my elements reacting with each other, I'm also moving electrons around. Now, not all reactions are redox. Some reactions, you're just moving elements, like swapping two pairs or something like that. So a double replacement, for example, you just swap two elements for one another and get two different compounds. So you won't necessarily have to use any electrons in doing that. The charges that already exist are sufficient. But for an element like sodium reacting with an element like chlorine, if we remember all of our chemical principles that we've studied up to this point, where we want to satisfy the octet rule, we want to have balanced charges and that sort of stuff, then we would see the only way to do this is to move this electron from sodium to chlorine. And thus, this would be a redox reaction. I'm going to write down some terms here. Sodium is losing its electron, and chlorine is gaining the electron. We have specific terms for this, and you can see those terms right here. We've got oxidation and reduction. When you lose electrons, that process is called oxidation. The word oxidation comes from the fact that oxygen loves to take electrons from stuff, and so if your electron gets taken by oxygen, it's called being oxidized. So it has nothing to do with oxygen necessarily, because all sorts of things take electrons. But if you lose your electron, you have been oxidized. If you gain an electron, you've been reduced. The reason that we use the term reduce or reduction here is because we're reducing the charge. The charge is becoming more negative. Now, we do have a mnemonic to help remember this in just a second here. There we go. And the mnemonic I use is oil rig. And so what oil rig stands for is if you are oxidized, you lose electrons. Oxidation is losing electrons. If you're reduced, you gain electrons. Reduction is gaining electrons. Oil rig. So what we're going to do is we're going to look at different reactions and examine the elements from the perspective of did it gain or did it lose electrons? So let's look at a simple example before we go on to these examples that the text has. So we're going to go over, if I can click on the right thing here. Here we go. We're going to go over here. And we don't really need this, so I'm just going to shove it in the corner real quick. I'm going to give you a type of reaction that you'll see in the textbook. So let me think here. We'll just do something like this. If you see a reaction that's kind of like this, so this is more or less the same as like sodium chloride, but you see elements as reactants, and then you see an ionic compound as your product, what you can do is you can examine the charge of all of these substances in the reaction. Now remember that elements are neutral, so if I ask you what the charge of an element is, don't immediately do this. Yes, calcium wants to make a +2 charge, but that's only when it's an ionic compound. What's the charge on calcium? Well, if it's by itself, it's nothing, right? That's because it still has all its electrons. How about bromine? What's its charge? Well, there's two of them, and I didn't write anything up here, so it's got to be 0. These are elements in their atomic elemental state. And we have to remember that when we have elements that don't have a charge or are not in an ionic compound and have broken apart from that, then the number of electrons and the number of protons in them will be the same, and thus their charge will be 0. Now over here we have an ionic compound. This would split my ions into these ions like this, right? And I just have 2 of these. So if I were to ask what the charge was, well, calcium with a 2+ is just +2. And bromine with a negative charge is that. So now what we're going to do is we're going to look at before and after. And this is going to be a common theme. We're going to look at before and after to determine a redox reaction. So what happened to calcium here? And what happened to bromine? So before, calcium had a charge of 0. Now it has a charge of +2. So to get to that, calcium lost 2 electrons. And so we would say that calcium was oxidized. What about bromine? It started at charge 0, and it became -1. So each bromine gained an electron. And so we would say that bromine was reduced. So we can do this sort of analysis on simple problems to determine whether something has been oxidized or reduced. Now, this is one type of oxidation-reduction reaction, where we look at the elements and then figure out what the charges are before and after. There are other types that are a little simpler that we're going to look at as well. So what I'm going to end up showing you are like structures that look like this. And your task will be to determine whether the reaction is oxidizing or reducing from reactants to products. Now, you might be looking at that and going, what the heck is this? So we'll try and explain this in a little more detail here. This type of structure where we have these like lines, this is called organic Lewis structure nomenclature. And so what organic structures try to imply is that, well, since we often write carbons over and over and over again, each corner or junction that's unlabeled we'll just do that. I know unlabeled isn't hyphenated, but is a carbon. So in other words, if I were to go over to here, we'll put this diagram on the screen here. Let's make this a little bigger so we can see it. We'll just put it over everything. If I were to draw that structure above this as R1OH, what it would actually look like is this. And then the other structure on the other side of the molecule would be this. And so you could see that this carbon right here that isn't drawn in the structure above is implied. And the reason that we do this is to save ink, basically. It's also to save you time when drawing stuff, because drawing little lines is a lot easier than stopping and drawing a carbon every time. Now, you'll notice, though, that this carbon right here doesn't satisfy the octet rule. There's only 2 bonds coming out of it. So whenever a carbon is drawn at a corner, or an endpoint, or whatever, and it doesn't look like there's enough bonds coming out of it, what we do is we add enough bonds to satisfy the octet rule, and those bonds are intended to be hydrogen. So that corner up there, where it goes R1, there's a little corner, and then it's like OH. That corner is intended to be a C with 2 H's coming off of it. Over here on the right, I've got a carbon, but it's already got 4 bonds, so there's no H's coming out of it. So this carbon is just a carbon. If I go to the next one down here, where it says R1, R2, there's my structure, where that red arrow is pointing at. Well, I only have 3 things bonded here, so I need a 4th one. And that's going to be my hidden H. And the H's are hidden because, again, they're just abundant, and we have them all over the place. And drawing them costs ink and time. So if we just assume that they're there, based on how we draw these structures, it'll save us some time. That's how we decipher these structures. And that's going to help you a little bit in lab number 5, which is going to come up next week. Now, back to the topic that we care about, oxidation reduction. When you oxidize something, it means that you're reacting it with oxygen. So that means that if you add oxygen atoms or bond oxygen more times, you are reacting with oxygen. So what we're going to do is we're going to look in our reaction and say, okay, before and after, do I have more oxygen atoms or do I have more bonds to an oxygen atom? If either of those is true, we've oxidized our substance. So on the board, I have highlighted in yellow here. On that carbon, there's just hydrogen on the left. But on the right, I've got my oxygen bonded twice to the carbon. I have gained an oxygen, so we would say that that's an oxidation. On the bottom, I have one bond to an oxygen, and then after the reaction is done, I now have two. So if I add extra bonds to oxygen, it's an oxidation as well. So that's what we're going to be checking for. Look for extra oxygens being added in, or look for extra bonds to existing oxygens. If either of those happens, the reaction is an oxidation. Now, what would the opposite process be? For a reduction, well, there's the spoiler. It accidentally appeared there. We want to get rid of oxygen, so we have to replace them with something, so we replace them with hydrogen. Now, you don't necessarily have to replace oxygens. You could just be adding hydrogen. So, adding hydrogen is our clue that a reduction has happened. Alternatively, we could just remove oxygen somehow. We're going to see some examples later where we turn like CO2 into just C. If you remove oxygen, that's also a reduction. All right. So here's my reactions that I want you to look at. Ignore these little like corners. I'm not really sure. Those are just artifacts when I copied and inserted these Lewis structures. So what I want you to tell me is for each of these reactions, and we'll number them. Again, just ignore these. I want you to tell me for reactions 1 and 2, which substance is oxidized and which substance is reduced. Or I'm sorry, let me try that again. I want you to describe reactions 1 and 2 as oxidation or reduction. And then for reaction 3, I want you to tell me which was oxidized or which was reduced. Was the Fe2O3 oxidized or was it reduced? Was the carbon oxidized or was it reduced? Type all your answers in the chat, and we'll go over the results in about 4 or 5 minutes. One more minute, we'll go over the answers. All right, let's go over here and let's see if we can fix this. So for this first set, actually, I don't even need to be on the screen, I realize. I can just do that from here. For this first set of reactions here, my carbon starts with no bonds to oxygen, but then it's bonded to oxygen 4 times, 2 on each side. So this must be an oxidation. It totally is. Over here, my carbon has 2 bonds to oxygen, but now there's only 1. So this must be a reduction, and it is. And then finally, down here, what was oxidized and what was reduced? So if we look at carbon, we see that it ends up as CO2. Well, I formed bonds to oxygen, so carbon must be oxidized. But if I look at iron here I have bonds to oxygen, and then at the end, I've lost them, so this must be reduced. All right, that's oxidation reduction. Let me know if you have any questions. That's the simple version of it anyway. It can get much more complex, but that's all we're going to cover for this class. All right. So remember that the rules for oxidation and reduction for oxygens and hydrogens will be pretty common in biology. There will be other oxidation reduction reactions out there that you'll just encounter as you see them. But for the most part, that's the simple short version of it. So we're going to move on to the next topic, which is collision theory. And I don't know where my little diamond guy went. He just kind of took off there. Nope, he's just going to nope on out of there. I must have like some old animation or whatever. All right. So this next section talks about how reactions occur. For a reaction to occur, you would think that we'd just mix 2 things together. So we'll mix A, we'll mix B, and then the reaction occurs, right? But in reality, what A and B have to do is they have to encounter each other. And that encounter typically involves a very high velocity collision, where A rams into B at blistering speeds. And one of 2 results may occur. So the first result is that A bounces off of B and nothing happens. Or the collision between A and B is so powerful that all the electrons get knocked around, and when they resettle, they form an arrangement that is consistent with bonding. And we get a reaction. So, depending on how the reaction occurs, some small fraction of collisions may result in nothing, or a very large amount of the collisions may result in nothing. And this is all going to influence the speed of the reaction, which we're going to talk about at the end of the chapter here. Or actually, maybe just a little bit, now I think about it. Now, here are the phenomenon that we need to consider in order for a reaction to occur. So the first reaction is, or the first condition is that we have to have enough activation energy. Activation energy is the minimum amount of energy for a reaction to occur. For example, if you strike a match, the friction from the match head reacts with oxygen or provides energy, which then causes it to react with oxygen in the air and then ignite on fire. The activation energy for the match is you striking it. You have to provide enough energy for the reaction to occur. If there was no activation energy, matches would spontaneously ignite on their own, and that would be very bad. You couldn't buy them or store them safely, right? I don't know how I would go to bed at night, every night, thinking about the matches. What if their activation energy is 0? Oh no, they'll ignite and burn everything down! Fortunately, that's not the case. So there must be some minimum energy for a reaction to occur. Otherwise, it would happen on its own, without any input from anything. The other issue that we have to consider is that the orientation of the molecules has to be correct. And I forget if I have a slide for orientation here. I don't, but what we'll do is we'll draw a picture. So we're not going to talk about orientation much, but we're going to do a very simple diagram here. So if I do NO plus Cl2, oh, I have this backwards, actually. Hold on. There we go. This is a common reaction that people use for this. So we'll go NO Cl. And then I have a Cl molecule. Actually, we'll do this one in red. Or actually, no, we won't. But what I'm going to do is I'm going to do this. And we're going to say, where should the reaction occur so that I get Cl2? Because I want this at the end, right? Okay, if I bonk into the molecule on this side, do I make Cl2? No, obviously I don't, right? Because the Cls don't make a bond. So anywhere over here, no good. But what about up here? If I bonk over here, now I can make Cl2, and then the NO can just pop off, right? So, if I am looking at this from the perspective of orientation, my collision has to occur somewhere, somewhere in here. So the thing that we're going to consider for orientation is just, oh, okay, my molecules need to bonk into each other in a logical way so that the reaction can occur. I can't form bonds through space. I have to form bonds by two atoms just being adjacent to each other when the bond occurs. So there are places on molecules where reactions will trigger, and there are places on molecules where reactions won't. They'll just harmlessly bounce off and nothing happens. All right. So that's how we deal with the consideration of orientation. We're going to spend the rest of this section discussing activation energy, because that's more relevant to us. Now, activation energy and the energy that is released from a reaction are valuable pieces of information that we should consider when looking at various reactions to do what we want. What we're going to do is we're going to draw a diagram, and the diagram is going to show us the input and output of energy for a given reaction. And that's going to look like this. We're going to draw a coordinate where on the y-axis I have energy, and on the x-axis I have reaction, and I'm going to put progress in quotes. Basically, we're going to have before the reaction on the left, during the reaction in the middle, and after the reaction on the right. And so what we're going to do is we're going to have some lines for reactants and products relative to whatever the reaction is going to tell us. And so these could be up or down. And then there's going to be some sort of curve in the middle to connect them. And our job is to understand what this curve looks like and why it looks like that. Now, obviously, I'm just drawing a random squiggle there. But our curve is going to depend on the nature of the reaction as written. Importantly, it's crucial to distinguish that all reactions will have an activation energy. In other words, I have to put in a certain amount of energy before the reaction will go. We'll show that on our diagram too. We're going to look at this reaction here. If I mix A and B, I produce some product AB, but I also produce heat. Heat is a form of energy. And if heat is released, then that tells you that AB must be lower in energy than A and B separately, because the difference between those two, the reactants and the products, is the heat that is released. So you could think of it something like this. Well, here's how much energy A and B have individually. Putting them together, I get AB, and then this would be, oops, sorry, it should be equal. This is the heat that is released. And so this heat is released, it's no longer in the reaction, and this is how much energy we have left. So let's just plot that on the y-axis. So we'll do that right here. So here's the energy of A and B. It's some amount. I've arbitrarily chosen to put it here. And then AB has less energy than its individual components because the reaction released heat. The heat that the reaction released must be this much. So by looking at the difference between the reactants and the products here, we can determine where the energy goes or is coming from. In this case, heat was a product, so I release the heat, and that means that my products are that much lower in energy. Now, what is this right here? Well, remember, I have to put in energy for the reaction to occur, so this must be the activation energy. So in order for this reaction to occur, maybe this is me striking a match on a matchbox. I provide this much energy. The reaction then starts, and I actually get this much energy back, which refunds the activation energy I put in there as heat. And then I get extra heat equal to the difference between the products and the reactants. Since I have to pay for my activation energy and I get it refunded, I'm only going to count this part as the heat released by the reaction. Because that's all we get back. We have to repay the energy that we've invested to get the reaction going. All right. This reaction released heat, so we're going to give it this term. An exothermic reaction means that the energy or heat, the thermic part, went out, which is what exo means. What would happen if you had an endothermic reaction? Let's consider that. An endothermic reaction would do the opposite. Energy would be absorbed. And so what I want you to do is consider what type of reaction that would look like. So you're going to do a reaction with A and B, and then heat is going to be in some part of it. So you're going to have something that looks like this. And you need to put the heat on some part for where the heat gets absorbed. What I want you to do is draw the energy diagram for this reaction. Assume, again, that there is some activation energy. So again, this will be for an endothermic reaction. So I'm sort of giving this to you. And then when we come back, we'll talk about hot versus cold. I meant to do it on the previous slide, but I wanted to jump into this exercise. So first, do these steps actually in reverse order, really. So do the bottom step first, write a chemical reaction, and then put heat somewhere in this reaction, and then draw the energy diagram for it. I'll check back in with you in about 3 or 4 minutes, and then we'll go over the answers, and then we'll talk about hot versus cold packs. All right, one more minute, we'll go over the answers. All right. So, first let's write out a reaction here. So if my reaction absorbs energy, that means that heat must be on the reactant side. And what our diagram will look like this. So here's our energy. E-N-E-R-G-Y. And so we're going to be adding heat to our reaction. So that means that A plus B must start down here. And when it's done, it'll be up here. And the heat that is added would be this much. Sorry, I have a throat lozenge because I'm just coughing all the time here. So you might hear me chewing on that. Now we have to include an activation energy. Now, if you draw something like this, there's no activation energy, right? Like, I would put in energy for this reaction to occur, but then the reaction would just go right back over this way. You can imagine these energy diagrams as like a sort of hill where you have a ball, and if the ball's on the hill, and there's nothing to prevent it from rolling down the hill, it's going to do that, and this is where the reaction will end up. But if I do something like this, where I put a small hill in the way, then if I have that ball at the top of the hill, it's going to fall over here, and then it'll stay here, because it won't just roll back down to the reactants. And so this little hump right here represents our activation energy. Now, the energy that you have to put in to get the reaction to occur is still relative to the reactants. So this would be the activation energy. And again, because the heat was added, this is endothermic. All right, last little thing to talk about before the break. For endothermic versus exothermic, there is a sensation associated with both. And so what we're going to do is we're going to draw an object, and then we'll put a little hand on it. So this is, like, we'll just say that this is your hand or something. Looks more like a golf club, actually, but that's okay. Or your paw, I don't know. All right, let's suppose that the object releases energy into your hand. The reaction would be exothermic if the energy is leaving the object, right? What would you sense this as? When you touch an object and absorb energy from it, that feeling is heat. Heat is the energy released from an object. So, touching objects that are undergoing an exothermic process, the sensation we observe is hot. But what about for endothermic? In this case, the energy would go into the system. And so the sensation you would feel here would be the opposite of heat, or cold. Oh, excuse me. So we can determine a reaction's energy diagram just by feeling it. If you mix two things in a test tube and you touch the test tube and it feels really warm, you go, oh, energy's being released. And so you know what the energy diagram would look like. All right. We're going to take a break while I go and try to, like, rinse my sinuses out or something because, oops, that's the wrong card. There we go. Because today I am just unable to, like, I have to keep hitting mute every, like, 10 seconds. This happened yesterday where my timer didn't load for, like, 30 seconds. I don't know what's going on. So, give my computer a second. It's tired. It's as tired as I am. Thinking. Come on, computer. I'll just start the music and we'll get the timer going. And whenever it appears, it appears. So, we'll see you in a little bit. Alright, we're back. Feeling a little better. I'm just chugging water now. Something I forgot to mention earlier is the homework practice for this section. So that is listed below here, so make sure to do as many of these problems as you can. Alright, let's talk about kinetics. Kinetics is the study of how quickly reactions occur. And this speed at which reactions occur is going to be based on the factors that we talked about before. How much activation energy is there? And what orientations of products will lead, or of reactants will lead to products. So, the speed at which a reaction occurs, we're going to call the rate of its reaction. And so, our job is to manipulate the rate of the reaction to do whatever it is that we want. For example, if a medicine is fast-acting, that means that you would experience relief from symptoms that medicine can alleviate. If the medicine acts more slowly, it may be able to provide relief for a longer period of time, but it would take longer to kick in. In some cases, you want relief as fast as possible, say, like, for instance, pain. In other cases, doing something more prolonged over time, so, like, you're going to take a medication before bed, and you don't want to wake up from, like, acid reflux or something. Then a more prolonged effect would be more called for. So we're going to examine different factors that will affect how fast a reaction can occur. And this is called kinetics. Kinetics is the study of how fast reactions can occur and how they can be controlled. We're going to look at 4 different ways to study kinetics in terms of things that we could do to tailor the reaction rate to whatever it is that we need it to do. And those 4 things are the following. So the first is the physical nature of the substance. Second, we're going to care about how much stuff we actually have, how concentrated the sample is of our compound. Third, we'll care about the temperature at which the reaction occurs. And then fourth, there's a special consideration called catalysis that we're going to explore on its own. All right, so let's look at a reaction between A and B, where A is a solid, and B is the solution that's reacting with. On the screen, I have shown 2 different samples of A that I have added to the beaker. On the left, I dropped a giant chunk of it in there. On the right, I ground it up into smaller chunks and then added that to the solution. Which one would react faster? It turns out that for a chemical reaction to occur, just like we had said before, reactions only occur where the substances can touch each other. So A has to contact B in order for the reaction to occur. So right in the middle here of this solid chunk, no reaction is going to be occurring right here. It can only ever occur along the surface of A. I have highlighted that area purple. Over here for the other chunks, I have also highlighted the outer edge in purple. That would represent this edge over here. Then what I did is I highlighted all the other edges a darker purple to show the increased surface area that the solution can contact solid A. The takeaway is that if I have more surface area present, I have more places for the reaction to occur, and thus the reaction should happen more quickly. So let's see this in practice. I'm going to load a video, and we'll see if my browser is up to date. Or nothing can happen. That also is a thing that could occur. Man, I love when nothing happens. It's not even opening in a window. Like, I don't even know what to do. PowerPoint has stopped responding. You know what? Sure, we'll close the program. So So give me just a second because PowerPoint has stopped responding. I gotta find where we were. We were here. So this should load this back on the screen. Oops. And then when I click this, really nothing is happening again. I hate this. I hate this so much. Oh, I love when my computer is just busted and does nothing. For no good reason. Okay, so why is there no... Oh my goodness, hold on. Edit hyperlink. Copy hyperlink. We'll do this the hard way. All right, there we go. All right, on the screen, I have 3 containers here. So I've got 3 beakers. So they all have HCl in them. And in these dishes is calcium carbonate. The instructor here has ground up these calcium carbonate pellets to varying degrees of fineness. And based on the reaction that you're going to observe here, your task is to identify which one was ground up the finest and which one is the chunkiest. So there's reaction number 1. You can see the solid chunks there. Here comes reaction number 2. You can see that's a little more vigorous. The bubbling is a little more intense. We'll make it bigger so you can see it. And then here's the last one. So looking at those 3 reactions, you could tell which one is ground up the most. And clearly it must be this one on the left. This one over here, you can actually see the solid chunks. There's not that much in there. So there's only a few pieces in there, and it's reacting very, very slowly. This one is sort of in the middle. All right, let's make that smaller because we're going to watch another video in just a second here. All right. Now, the next topic that we talked about was concentration. How much concentration affects the reaction rate is going to depend on your reaction. But in general, this would be true. If I had 2 solutions, and I had them each poured into a 1-liter beaker, I put 1 mole of both A and B versus 1 mole of A and 4 moles of B. If I have more B and A and B are my reactants, then increasing the number of opportunities to react should increase the speed at which the reaction occurs. In the first situation, solution 1, any molecule of A will have a 50-50 chance of bumping into either another A where no reaction occurs, or another B where a reaction will occur. But if I look at that from this other perspective here, if I have the same amount of A in a solution with 4 times as much B, I have more opportunities for the reaction to occur. So increasing the concentration increases the likelihood that I get meaningful collisions that will lead to a reaction. Now, whether this is a solution in an aqueous phase or it's in the gas phase, doesn't matter. It all operates by the same principle. The more collisions that you have that can potentially cause a reaction, the faster the reaction goes. All right, I don't have a video for that one, but that's okay. Let's talk about temperature. We have talked about temperature a fair amount in Chem 121. We know that temperature is the speed at which molecules move. If objects are moving faster, they have more energy. So adding heat will cause molecules to collide with more energetic collisions as a result. You could think of this as throwing a tennis ball at the wall versus launching it from like a cannon. Which one will do more damage because it has more energy? Well, the one that's launched at a higher velocity, right? So if this is our reaction diagram for just a generic exothermic reaction, at a low temperature, maybe the average energy is simply this. Like, here's the average energy of our molecules. So, on average, the molecules don't have enough energy for the reaction to occur. Very small number will get over the activation energy, and so the reaction will go very, very slowly. But if I heat this up so that the average energy is now up here, now most of my molecules have enough energy to react. And if most of my molecules can react, then I get more products. So increasing the temperature increases the likelihood of reaction. I do have a video for this. Let's see if this one loads. I can't believe that none of my links are working. What is going on with my PowerPoint today? Hey, guess what's going to happen? It's going to crash again. Oh, maybe it won't. No, now it crashed. Okay, hold on. Close the program. Ah, my goodness. I'm just going to have to reboot my computer between classes here. I'm not on slide 10. Stop it, PowerPoint. Where am I? I am here, so we'll get this on the screen. And then I have to dig into the PowerPoint too. So edit hyperlink, copy. And we'll paste that in here. All right, there we go. All right. So we have two glow sticks here. And what we're going to do is we're going to immerse these into different beakers that have different temperatures. So they should have the same brightness, although in my opinion, oops, I didn't mean to like the video. I feel like the one on the right is a little less bright, but in the middle, they're pretty comparable. So what we're going to do is we're going to put them into two beakers with different temperatures of water. Now, one of these is hot water and the other one's cold water. You can probably guess which one's cold water by the condensation on the right here. But what I'm going to do is I'm going to pause this video, and I'm going to sort of just fast forward by going like this. And can you see the effect as I skip ahead every 5 seconds? I think the difference is more observable over time here, so I'm going to go back. So we're going to go forward again. And you can see as the temperature of the one on the right goes down, the glowing, which is the reaction we're observing here, fades out. Whereas on the left, when the temperature increases, the glowing intensifies. So by increasing the temperature, we could speed up the reaction and make the glow sticks brighter. Now, when I was a kid, what I was told when I was given glow sticks at like 4th of July or whatever was that if you want to preserve them, you put them in the freezer. And so that's what we would do, is we'd throw them in the freezer, and then we'd never take them out again. And then for years, there was just glow sticks in the freezer, right? But they'd be very, very, very faint because the temperature was very low. The reaction was suppressed. It was slowed down. All right, the last thing that we're going to talk about is the catalyst. A catalyst is a substance that causes a reaction to occur at an accelerated rate. But, very importantly, it does that and more. The great thing about a catalyst is that catalysts are not used up. They can be reused. A catalyst is not a reactant. It is simply an opportunity for a reaction to pursue a different chemical pathway. What that means is that if I have a reaction that requires a lot of energy to occur, using the catalyst may cause it to require less energy. And as a result, the reaction is more quickly able to occur. Here is an uncatalyzed reaction. We've seen this diagram before. If I have a catalyst in my reaction, the energy diagram will change appropriately. When I add the catalyst, I change the activation energy. And by doing this, I end up with a faster reaction than I normally would have. And so this leads to very, very powerful control over doing chemistry. If you can discover the correct catalyst for a reaction to occur, you can do all sorts of things. One of the most important reactions that requires a catalyst is the production of plastic. Plastic is not something that we can find in the environment. It's not something that naturally occurs. But if we take certain chemicals and expose them to a catalyst, we form plastic immediately. In fact, the reaction is so fast you could do it right before your eyes in a laboratory. And I've done it before as part of a third-year chemistry class. It's really neat to do. We're going to look at a different catalyzed reaction. This is called elephant toothpaste, and you'll see why. This is the reaction of hydrogen peroxide decomposing to water and oxygen. This reaction will occur on its own, but it's extremely slow. Hydrogen peroxide is sold in these dark bottles, and then you store it under your cabinet where it's temperature controlled because we don't want it to decompose. We want it to stay hydrogen peroxide so we can use it for like cleaning wounds and stuff, or gargling, or what. If we add a sodium iodide catalyst to it, the decomposition occurs much more quickly. And so we're going to explore this in the last video that I have for kinetics, which I have to get out here because if I click on it, it will just crash. All right. This one I'm going to actually put the volume on for, and I know it'll probably ding my video for a copyright strike, but it's worth it. You may have heard of this guy. His name is Jimmy Kimmel. And the guy on the left is Science Bob. Science Bob does this reaction all the time for various people. He does demos. And in fact, I believe Science Bob has the world record for the largest version of this experiment, which involves a swimming pool. You can look that one up on YouTube. But I'm going to play this video for you. We'll turn up the volume and... Oh, we got to turn it up here. Here we go.
So, all right, so what do we do?
We're going to get started. We're going to start with a little bit of, actually, dish soap. So if you want to put some dish soap in your flask.
How much? Just a squirt?
Yeah, a little more. That's.
Well, wait a second. Dish soap wasn't part of the chemical reaction. We're going to add dish soap to capture the oxygen gas that's released and trap it in bubbles. The dish soap makes the reaction fun. It doesn't actually participate in the reaction. It's just sticky enough that gases get trapped in it, and it will then expand, and then we can see that. So that's what the dish soap's for. Also, I'd like to comment that every time a liquid is added to a flask, music starts playing, and I feel like this is how everything should be in life.
Good.
Okay.
So dish soap will keep the bubbles, because we're going to remove the oxygen, and they'll hold the oxygen.
Okay.
There. So I'll put a little bit in here. All right. Next, coloring. We have green and red. Do you have a preference?
I'll take red.
All right.
It's be very Christmassy. How much of this?
And just keep going. Keep adding a lot of that.
Okay.
That's good. A little more.
This is going to be delicious.
All right.
Is this how you did your jacket?
That's good there.
Okay.
All right, so I'm going to add the hydrogen peroxide because you don't want to do that.
Okay. Oh, it's dangerous,
This
right?
is
Okay.
and actually, yeah, let's get all geared up here.
Okay, good. Put these on my eyes.
There we go. All right, so in goes that. And
Now, what's happening here? What process are we about to see?
So here's what we're going to see. We're going to, in order to remove the oxygen, we're going to use a catalyst.
Okay.
The catalyst will speed up the reaction. So we're going to, that's what's in here. It's a sodium solution. We're going to pour that in, and that's going to remove the oxygen. The soap is going to hold it,
And we're going to smother to death, all of us.
It'll be okay, but it will create a lot of bubbles really fast.
Okay, great.
And usually this is done in graduated cylinders, but we're going to make it a little more intense with these ridiculously large flasks.
Okay, good.
All right. So this is what you're going to use. We're going to pour that in there. The oxygen will be released, and we'll watch the reaction. We're going to need to step back after we pour it.
Okay.
All right. Here we go.
Step back.
Ready? In 3, 2, 1, pour. There we go.
Whoa! Whoa! Wow, that's great. It's like Ghostbusters. Wow. Whoa! That's something.
And that camera was ruined, or that light, or whatever. So, we do this reaction for the science fair, or specifically I do it, for a bunch of 5th graders. And like 80% of the 5th graders are like, oh, that's the best thing ever. We love elephant toothpaste. And then the other 20% are like, that sucks, because they're 5th graders, right? They don't want to be there. They just want to go home and play, I don't know, Minecraft. Oh, God, I sound like an old person. Kids these days don't appreciate science. Anyway, those are the 4 things that we can do to control the rate of a reaction. So there's our summary. So on the screen, I'm going to put a problem up here. I'm going to put 2 problems, actually. So the first problem is, why do you think we store milk that we purchase from the store in a sealed container in the refrigerator? So think of what reactions milk can undergo. And then give 2 reasons why we do these things to prevent those reactions, because you don't want reactions to occur in your milk. It would sour and get gross. And then the next question I have here is, a scientist devises a reaction. It reacts with water, and it turns the solution dark blue. But the reaction only works for 10 minutes. Let's suppose that the scientist wants the reaction to last longer. What could she do? And if the scientist wants the reaction to go faster, what options are available? So go ahead and answer these questions. We'll go over the answers in about 5 minutes, and then we'll move on to the next section. 1 more minute, we'll go over the answers. All right, let's go over the answers here. All right, so for the first question up here, why would we refrigerate milk? Well, we don't want the reaction of milk with, like, say, oxygen or the environment or whatever to occur, because then it will spoil more quickly. So let's just clear all this out. So if this is my milk jug, when you fill it with milk, something that occurs is that there's a very small headspace. And that headspace is where the oxygen will be when you open the milk bottle. If we minimize the surface area, then what we end up doing is we reduce the opportunity for the reaction to occur between oxygen and milk. Now, the other thing that we do is we put it in the refrigerator where it's cold. And the result of that is that it lowers the speed of the reaction for the decaying or fermenting or whatever process that we don't want. We don't want it to go bad. Excuse me. All right, so that's the milk. For part 2, the question with the scientist, if I want to slow the reaction down or speed it up, we can do various things to it. So if I wanted to make the reaction last longer, we would want to lower the rate. And so what we could do is we could do each of the 4 things. So we could... The first one was surface area, so we could use larger chunks. We could have a diluted solution or less concentrated. We could lower the temperature. Or we could not use a catalyst. So those are all things that we could do to make the reaction go slower and last longer. Finally, if we wanted to make the reaction faster, we could do the opposite of these things. So we could grind the substance into a powder. It's already a powder, so we'll say it's more fine. We could concentrate the solution. We could heat it. Or we could employ a catalyst. All right, any questions, let me know. There's the homework practice. All right. I realize that there is 15 minutes left in the class. However, I'm not going to have enough time to go over these topics, and I did just have something come up that is going to need my immediate attention before my next class begins. So what I'm going to have to do is I'm going to have to link a video from a previous quarter to do these two sections here. So these two sections will be in a separate video on the 121 playlist. And I'll try and get that set up in a little bit, but I have to deal with something in the next 30 minutes before it becomes too late to deal with it. So I apologize that I have to stop the lecture early. But that's all that I'm going to have time to do today. The video that I link will cover the rest of Chapter 9. And then the quiz will be put online for Chapter 9 so that you can take it. And it will be due Tuesday. All right, I do want to thank everybody for coming out to the video, and I do have to get going, so I'm just going to go straight to this music here, and I'm just going to hit play. And I'm probably going to sneeze, so I'm just going to mute myself. Have a wonderful weekend. I'll get that video up online soon. Let me know if you need anything.